Okay, we're going to do another brief video talking about Newton's third law this time. So we've probably heard every action has an equal and opposite reaction, and that's what this is all about. It's about force pairs. In Newton's third law, we say for every action force, there's an equal and opposite reaction force, meaning that forces end up working in pairs. So for every action force, there's an equal in size or magnitude and opposite in direction reaction force. It is very poetic, isn't it? We've all heard this one. For every action, there's an equal and opposite reaction. Very, very cool. But should we look at an example? How about a rocket ship? Rocket is a great example of Newton's third law because the action force is the rocket is firing gases out of the exhaust, and they're pushing down on air. The reaction then is the air pushing back up on the rocket. How about another one? There's a little birdie delivering a baby. The action would be the wings flapping, right? And the wings are pushing down on the air. But the air is pushing up on the wings. About the cute little turtle here. As the turtle crawls along, there's an action with the feet. They're pushing back on the ground or the floor. But the floor is pushing forward on the feet. And we get some turtle motion there. These force pairs exist in everyday life. If you're trying to be cool, leaning against your locker, you're pushing on the locker, and the locker's pushing back on you. You're sitting in your chair, you're pushing a force of your weight on the chair, but the chair is pushing back up on you as well. Swimmers use this when they kick off of the wall in the pool. They're kicking the wall, and the wall's pushing back on them. Squid use this when they want to make a quick escape, like a jet. They shoot like a jet of water out of their back, and then the jet pushes back on them. What I'd like you guys to do is take a look at this picture, take a long look, and try to identify 6 of the action-reaction forces in the picture. There are 6 action-reaction forces in this picture. Do that now. Okay, we're back. We've got a bowler that has an action and reaction. So the action reaction means in the bowler example, the bowler and the ball get equal and opposite forces when the ball is launched. But the bowler has such a larger mass. So since the bowler's mass is greater than the ball's mass, the bowler accelerates less than the ball. So if you draw sort of a proportion between them, although their forces have equal magnitude, opposite directions, their masses and accelerations are unequal. The mass of the bowler is much larger, but the acceleration is less. The mass of the bowling ball is much smaller, but it accelerates much more. And remember, acceleration is the cause of motion. Forces cause acceleration, acceleration causes motion. And we're back with Rudy and his buddy Fat Albert. So we want to get cart B to go the greatest distance. Who should go on cart B? Should it be Rudy or should it be Fat Albert? You can answer this now. Who do you think should go on cart B if you want to go the farthest distance, Rudy or Fat Albert? Well, Newton's laws is going to explain what happens. Obviously, in the first law, we say that object at rest wants to stay at rest. So neither cart is going to move unless it's pushed or pulled. And in the second law, the object's acceleration depended on its mass and the force acting on it. So Fat Albert, having more mass, should not accelerate as much as Rudy. In Newton's third law, if we consider a force pair for every action force, there's an equal opposite reaction force, they will be pushed with the same force, but in opposite directions. And it sure does look like Rudy goes a farther distance, doesn't he? All right. Let's do these examples of Newton's third law. You got a fish swimming through water. Explain how that matches up with Newton's third law. Do a bird flying through the air, and do a car moving forward.